So this is a continuation about nano scale properties of matter. The presentation again was primarily put together by the University of Pennsylvania and NanoSense. So scale changes everything from a material property standpoint. Four important ways in which the nanoscale materials may differ from macroscale materials are gravitational forces become negligible and electromagnetic forces dominate. And this is because the mass and size is so small for nanoparticles. Quantum mechanics is the model used to describe motion and energy instead of the classical mechanics model. So, in most of physics, you guys were really looking at the classical mechanics and then rather than the quantum mechanics. The classical mechanics is like the things we can see, like how if you throw a baseball, how is that going to act? Greater surface area to volume ratios. So, the surface to volume ratios are just super huge. And finally, random molecular motion becomes more important at the nanoscale. So the dominance of electromagnetic forces. Because the mass of nanoscale objects is so small, gravity becomes negligible. And this is particularly because gravity is a function of mass and distance and is therefore very weak between low mass nanosized particles. So gravitational forces are almost zero, so they're negligible. Electromagnetic force is a function of charge and distance and is not affected by mass. So electromagnetic forces can be very strong when we have nano-sized particles. The electromagnetic force between two protons is 10 to the 36 times stronger than the gravitational force. And these forces become very important when we're talking about nanoparticles, and especially when we try to manipulate nanoparticles. Another characteristic is super high surface to volume ratio. So this ratio shows the formulas for the ratio of the surface of a sphere divided by the volume of a sphere, right? Surface over volume. And so most of these numbers can cross out, and what you end up with 3 divided by the radius of your particle here. If your particle is nano-sized, it'd be like 3 divided by 1 times 10 to the negative ninth, right? Which is a nanometer. This would be a number of like 3 times 10 to the ninth. So 3 billion, the surface to volume ratio. So the ratio is very big when R is very small. Another way that you could look at it more visually is to take a cube, say a 1 millimeter cube, 1 millimeter on each side. And if you were to calculate the area of this cube, it would be length times width, which is 1 times 1, and there are 6 sides. So times 6, and that's 6 meters squared. If I just cut this in halvesies, like all directions, I'll get 6 times, for one of these little cubes, 6 times 0.5 squared. And then I have to multiply that by 8 because there are 8 little cubes, right? And so that's 12 square meters. So I've doubled it. Let's say instead of halvesies, I cut them into thirdsies. And now I have 18 little tiny cubes. And so my surface area becomes 18 meters squared. So I have the same volume. The overall size of this cube is the same. I just keep opening up more and more surface areas in between where all these like crevices are. And it could really, really add up quickly. So as a surface area to volume ratio increases, there's a greater amount of substance comes in contact with the surrounding material, and this results in better catalysts since a greater proportion of the material is exposed for a potential reaction. Also, other properties change when you have so much surface to volume ratio, but yeah, it's great for catalysts. So this gives you an idea of the percent surface atoms, the percent of surface atoms based on over the diameter of the particle. So if we start getting into the 1 to 10 nanometer range, right, we have like 20 to way, way over 60% of the atoms are right on the surface of that particle. That's really crazy high. Whereas if we have 100 or 1,000 or 10,000 nanometer diameter, you have almost like very, very, very small percentage of the atoms are actually on the surface. And let me just go to this one. This kind of shows it kind of in an animated or cartoony way. So in a macro particle, almost all of the atoms are inside of the objects, right? So you have a lot of dots and not that many comparatively on the outside. But at the nanoscale, right, the number of dots inside and the number of dots outside are a lot closer. So you have a lot higher percentage of the surface atoms at nanoscale, which is what we saw. And then doing that, changing the object size has a very small effect on the percentage of atoms on the surface because there's just so many in the middle. But a change in size at the nanoscale has a big effect. And so this is one particular property of melting point doesn't depend on mass or size, as you guys know. Like one drop of water will boil at 100 degrees Celsius, and one huge pot of water will boil at 100 degrees Celsius because the boiling point's the same. But for teeny weeny nanoparticles, that is not the case. The smaller the particle, the lower the melting point. So I'm kind of jumping the gun there a little bit. But anyway, big, big differences. Okay. So as I start to talk about physical properties do change, the melting point of a substance will change at the microscopic scale. Why is that? We talked about the number of atoms on the surface of the particle is pretty high for nanomaterials. And if the atom is inside, then it's in contact with a lot of atoms, say 7 atoms in this little illustration, versus if it's on the surface, this particular atom is only in contact with 3 atoms. So because of that, the surface atoms require less energy to move because they are in contact with fewer atoms, and therefore the temperature of the melting point is lower, depressed. Okay. Here's some specific data, an example of the impact of particle size on melting temperature for gold. So you guys know that gold melts at a pretty high temperature. So here we're looking at 1300, roughly 1300 Kelvin, which would be about 1,000 degrees Celsius, give or take, right? 1,000 degrees Celsius. So if you get a nanoparticle, a particle of gold that's as small as about 20 nanometers, you bring the melting point down to about room temperature. So 273 Kelvin is equal to 0 degrees Celsius. So 300 Kelvin is about room temperature, give or take. So this thing says the melting temperature gets lower as a nanoparticle gets smaller because higher percentage of atoms are on the surface. This makes sense since the surface atoms are not bound to each other the same way bulk atoms are. It's really kind of interesting. I really like this video. I'm going to go ahead and show it within the video, a video in the video. And in order to do that, I have to share my sound. Here we go.
So here we have a gold nanocone and at room temperature, and we're applying an extremely high electric field around the apex here. And now we can actually see how these last 3 or 4 layers actually go into a surface melted state. So you can see how these atoms are moving around a lot more compared to the upper part of the gold nanocone. And so this is actually, what we see here is surface melting at room temperature.
Surface melting at room temperature right here at the tip. Okay, so I already showed you that one to describe it. So very, very interesting. Can you imagine gold melting at room temperature? It's crazy. All right, surface forces dominate over bulk forces for nanoscale materials, nanoscale particles. So bulk force importance decreases with decreasing volume. We've already said that. Or mass, same. Surface forces importance increases with decreasing volume. Quantum effects are also become more important at the nanoscale. So classical mechanical models that we use to understand matter at the macro scale break down for very small particles, nanoscale particles, or very fast materials, so things that go at near the speed of light. Quantum mechanics is better to describe phenomena that classical physics cannot. So, for example, the color of nano gold. So why isn't nano gold just gold, right? What makes it not be the gold color that we're all used to? Also, um, we'll learn in the next project in chemistry the probability of where an electron will be found. That's better explained with quantum mechanics than classical mechanics. So this is an example of quantum mechanics colloidal solutions of nano gold. So the nanoscale colloidal particles in the solutions seen above, these here, will never settle out. So just think, if you put gold flecks in water, right, eventually those gold flecks will settle down because they're pretty big. But these are nano-sized, and so they're so small, as we said before, the force of gravity isn't significant. So they're not going to settle out, assuming that they don't agglomerate into bigger particles. And also the colors change due to something called quantum confinement. So the particles are so small that the electrons don't have space they normally would have. And so it changes the way, light it then bounces off of the particles. And so we see them as different colors. And so that is basically what the ancient artisans used for stained glass windows and the Curtis Club. Did they know the stuff about quantum confinement? Of course not. They just knew that if they did certain processes that the glass would be very cool colors. But that's what they were actually doing. Okay, another change in property, a chemical property change with increased surface area, is reactivity. Okay, I like this one on the right really a lot because this is one of the few videos that I saw that shows not only the high surface area material, which is basically the steel wool, because that steel wool is so thin that the surface area is really high, versus a low surface area iron. Steel wool is basically iron, which she shows you in the bar as a piece of a little bar of iron. Oh, so yeah, here we go.
Let's look at the rate of the reaction of a very large surface area. Now with a small surface area, you can see we don't get that fast reaction.
Almost nothing happens. This video I also like. Again, we're looking at the steel wool or iron being able to burn. Oh, let me just show it. Iron being able to burn.
What happens to the mass in this chemical reaction?
With just a little match, basically, a little wooden stick that's on fire. So the temperature that they started that with is not very high, comparatively. And look at the iron is reacting, it's burning. Now this, I love also as a chemistry teacher, I love this video because if you do look at the mass, what would you expect if something burns? This doesn't have anything to do with nanotechnology, but you'd expect, when things burn for the mass to decrease, but actually this mass is, and in chemistry, when we get there, we'll find out why. But yeah, so high surface area is much more reactive than the metal bar here, which has a low surface area comparatively. Okay, here's another effect of the nanoscale is that random molecular motion is significant. So all molecules randomly move, and especially gas molecules, they move in this thing called Brownian motion. They're always like zipping around. So tiny particles like dust move about randomly. And at the macro scale, we barely see the movement or why it moves. And frankly, it doesn't really make a big difference, right? At the nanoscale, the particle is moving wildly, batted about by smaller particles, and it can really affect things, especially if you're trying to manipulate things at that scale, if you got things like randomly moving around. We've already started to talk a little about quantum mechanical effects. So some quantum mechanical effects are that electrons can only have certain energies in atoms due to the quantum mechanics. Semiconductor nanoparticles can behave like man-made atoms and have only certain energies allowed for electrons. That's super cool. The energy difference between these allowed energies in nanoparticles gets bigger as R gets smaller. So as the radius gets smaller, the energy gets bigger. Surface forces dominate over gravity as gravity's importance decreases with decreasing volume and actually its mass, right? So gravity is related to mass, is affected by mass. So decreasing the volume, you'll be decreasing the mass and therefore decreasing gravity's importance. We talked about that already. The surface force importance increases with decreasing volume. And we've already talked about that as well. So as you decrease the volume, or the size, right? More of the, much higher percentage of the atoms are on the surface compared to the middle than if the size of the particle is humongous. So surface forces increase with decreasing volume. An example of an impact of size is semiconductor quantum dots. When excited by light, quantum dots fluoresce or re-emit light. The size and material composition of nanoscale quantum dots dictates the color they re-emit. And they use quantum dots, I'm pretty sure, in like newer TVs. They could really fine tune the colors that come off of these quantum dots based on the size of the quantum dots themselves. The importance of wave properties of light. So all these things are like mixed in because you know the colors, yes, they're optical properties, but they also have to do with the wave properties of light. So the wavelength of visible light is much larger than the sizes of nanoscale structures. So wavelength of properties of light, you could look it up. It's something like 400 to 700 or 800 nanometers, in that kind of range. Because of this, light scatters and diffracts when it interacts with nanostructures. 700 to 400, yep. And so the typical sunscreen zinc oxide particles are between 100 and 10,000 nanometers in size, right? Clear nano sunscreen, the zinc particles are less than basically 200 nanometers. So they're less than the wavelength of visible light. So therefore, it's like it goes on like invisible, right? It doesn't go on white. Like in the olden times, when you put zinc oxide sunscreen on, you had this white layer on you, or you've seen it in movies where they have white stuff on their nose. And now you could use the nano zinc oxide particles and it's clear, so you can't even see it. Man-made nanostructures can cause light to turn sharp 90 degrees corners as seen below. That's wild. Wave properties of light. Nanostructures can cause light of different colors to scatter and diffract differently. This effect is used by nature to give the colors seen by butterfly wings. So at different magnifications, there are different colors. Beautiful. We talked about gold a couple of times already. So gold, bulk gold appears yellow or gold in color, right? Nano-sized gold is red and also can be other colors. The particles are so small that electrons are not free to move about as in bulk gold, quantum confinement. Because this movement is restricted, the particles react differently with light. Here's another slide about zinc oxide, is what I told you, right? This is the old traditional zinc oxide where it's white, and but the new nanoparticle zinc oxide looks clear on your skin. But they both block the UV light. So nowadays, sizes of, well, not nowadays, nanoparticle sizes are approximately the same as biological structures. We can now easily make structures in the 1 to 100 nanometer size range. Easily, I don't know, I'd say easily, but they do it often. This is the size range of many of the key structures in biological systems, like here's an example. So the cell is a complex structure with many compartments and organelles possessing individual and interdependent functions. Many of a cell's features, such as the pores and, of course, DNA and RNA, are in the nanoscale. We can now make structures like these smallest of features in a cell. And, some of these nanostructures that they make by attaching different like nanostructures on the outside help, like they can guide medicine to a particular tumor and have it attached to a tumor and stuff like that. I think I'm going to stop here. These are a lot of specific examples of nanomaterials, and I don't think that I want to go over those. I guess if you look at this slideshow, you can see the key points that we wanted to make through this slideshow are: nanostructures are extremely small, so small that gravity is not an important force in the nanoscale world. Nanostructures have large surface to volume ratios, which affect properties from their chemical activity to their melting temperature and optical properties. Nanostructures are so small that quantum mechanical phenomena can become very apparent. Nanostructures are so small that phenomenon resulting from the wave properties of light can become very apparent. Nanostructures are so small that they can have unique chemical bonding. Their size corresponds to macromolecules, so like molecular sizes, right? And the nanostructures are so small that their size corresponds to that of basic structures in biology. Nanotechnology has provided us with new tools to see the universe we live in, has given us new epistemologies. And that is it. Thank you for listening.